Alright, so we're taking a look at section 3.4 now. This is the diet problem. We're going to do it a little bit differently than the book. The book uses a human diet. We're going to see here that it doesn't need to be a human diet. It could be a farm problem. And so in this case, we have a farmer raising some pigs for market, and they would like to determine how much feed to use. And so we want to, of course, minimize the cost of the feed, but still maintain a recommended level of nutrition. Consider the table below with 3 types of feed in kilograms. Given are the units of each type of nutrient per kilogram, and to the right are the minimum daily requirements. Okay, so here's our table. And so given corn, for example, if I'm looking down the first column here, 90 units of carbs per kilogram, 30 units of protein, 10 units of vitamins, whatever that is. Okay, we're simplifying the problem quite a bit. Similarly with tankage, whatever that is. I'll let you look it up. Okay, so that we have 20 units of carbs per kilogram, 80 units of protein, 20 units of vitamins. So it's a little more vitamins here. Alfalfa, boy, it's loading up on the protein and the vitamins for us, and lower on carbs. And so the minimum daily requirement is listed here in the last column: 200 units of carbs, 180 of protein, and 150 of vitamins. So we want to use that information to try to minimize the cost of the feed. And so down below here we have the cost in cents for each kilogram of either corn or tankage or alfalfa. Good. So you might go ahead and pause the button here and see if you can write down what the LP should be, the linear program. Okay, so we'll continue with the linear program now. We want to minimize the cost. Before I do that, we should define our variables. Let X, Y, and Z be the kilograms of corn, tankage, and alfalfa, respectively. I'm kind of writing funny here. Okay, so then the LP, we'll try to minimize our cost, which will be 0.35x plus 0.3y plus 0.25z, such that, and now basically we're just writing down this table. So we have 90x plus 20y plus 40z should be greater than or equal to 200. Then we have 30x plus 80y plus 60z greater than or equal to 180. 10x plus 20y plus 60z greater than or equal to 150. Then we also have x, y, and z. Oops. X, y, and z greater than or equal to 0. Good. Alright, so that is our linear program. For good practice, you should try to put this in Lindo. Basically, you just write down exactly what you see here, except for the such that is just ST. Okay, everything else goes along. I would not put the x, y, z greater than or equal to 0, because that's kind of an optional thing in Lindo. But yeah, if you do that, you'll be able to see what kind of a problem we're going to get. Very good. All right. So most of the problems in this section are very similar to this. There's not too many homework problems. The first homework problem is 3 factories over, 3 factories, 2 pollutants, and we're going to be producing some, or we want to try to minimize or reduce the pollution. Okay, let's see, I think we have some time to try that one out, so I will write it down and we'll take a quick look. Alright, so here's example 1. from section, or exercise 1 from section 3.4. We have 3 factories on the river, factories 1, 2, and 3. Each factory is producing 2 pollutants. If the waste from each factory is further processed, we can reduce the amount of pollution. Right, so how are we going to do that? If the waste is further processed, we can reduce the amount of pollution by pre-processing or processing the waste further. So here's the 3 kinds of things we can do. So if it costs us $15 a ton working with waste from factory 1, and factory 1 reduces pollutant 1 by 0.1 tons. That's per ton of stuff that's being processed, and pollutant 2 by 0.45 tons. Okay, we can further process the pollutant from factory 2 by $10 a ton, and that reduces pollutant 1 by 0.2 and pollutant 2 by 0.25. I left those off of there. And similarly, $20 a ton from factory 3, 0.4, 0.3 tons are the reduction for that. We want to reduce pollutant 1 by at least 30 tons and pollutant 2 by at least 40 tons. Set up the LP. So again, what you might do is pause here and see if you can come up with a reasonable linear program to do this, and then come back and check to see if your answer matches mine. Okay, are you back? Let's take a look now. So we're going to go ahead and let x1, x2, and x3 be the tons of pollutant that we're going to process from each of the factories. Okay, so whoops, sorry about that. Now to process the waste, it's going to cost us $15 for factory 1, 10 from factory 2, 20 from factory 3. So therefore we want to minimize that cost. So we will minimize, I'm going to let x1, x2, and x3 be the tons that we're processing. We're going to take 15 x1 plus 10 x2 plus 20 x3, such that now my first constraint will be for pollutant 1. Pollutant 1, and then the second one will be for pollutant 2. So for pollutant 1, how much pollutant 1 am I getting? Or how much am I reducing it by? I'm reducing pollutant 1 by 0.1 tons out of each ton from factory 1 that I process. So that means I'm getting 0.1 x1, and then here I'm getting 0.2 x2, and here I'm getting 0.4 from x3. And so that's going to be the number of tons of pollutant that I'm reducing, and I want that to be at least 30 tons, right? So that gives me my first constraint. I've got 0.1 x1 plus 0.2 x2 plus 0.4 x3 to be greater than or equal to 30. So you can see what we're going to do next is exactly the same thing for the other pollutant. 0.45 x1 plus 0.25 x2 plus 0.3 x3 is going to be greater than or equal to 40. And then finally we just want x1, x2, and x3 be greater than or equal to 0. Very good. And yeah, I will leave it to you to decide if the 4 LP assumptions are satisfied for this problem. Very good. So that is the end of 3.4.